the screen here, so that should be fine.
Okay.
So probably we can start. Hello everyone, welcome to the Math and the seminar. So today we will have an interval seminar afternoon. The first speaker today is Colin. Colin is Colin is not very well, so he will give us a Zoom Zoom talk. So Colin will talk about what that? Sorry. Colin will talk about the group action on trees with T's independence property. Colin, you can share your screen.
Yeah. Thanks, main fun. Yeah, so everything I'll be talking about today is joint work with Simon Smith. Okay, so I need to start with some setup. So for this talk, now I can see some of the audience. So for this talk, a graph consists of a set of vertices and a set of arcs with maps, origin and terminus maps from the set of arcs to the set of vertices. And I want each arc to have a reverse arc. So there's an edge reversal map. And it has the obvious condition that the reverse of a reverse is the arc you started with, and it flips origin and terminus. And one slight departure from the definition of Serre is I want to allow the case where an arc is its own reverse. That means it would have to be a loop. It would have to have the same origin and terminus. So in the case of a loop, it's possible that the arc is its own reverse. It's possible that it's not its own reverse. And then a path through a graph is just a sort of sequence that of arcs that doesn't backtrack. And an automorphism of a graph is what you think it is. It is a map from the set of vertices and arcs to itself that sends vertices to vertices, arcs to arcs, and commutes with the origin, terminus, and arc reversal maps. So it preserves all the structure. Okay, so I'm setting that up now because I'm going to be talking about some graphs fairly generally later. But a special case is a tree, which is a graph where there's exactly one path between any two vertices. So another way of saying this is it's connected and acyclic. Like there's no multiple edges, there's no circuits, but you can get from any vertex to any other vertex. And so this talk is about groups acting on trees. You can define trees in other ways. This is just the most convenient combinatorially. And often an infinite tree will admit an action of a group of automorphisms that doesn't fix any vertex or edge. So the tree has to be infinite for that to be the case. And these are the sort of non-trivial actions from a geometric group theory perspective. Okay, so the classic approach to groups acting on trees is called Serre theory from the 1970s. And basically, you think of the action as built out of the orbits of the action. So given a vertex or arc, what are all the arcs or vertices it can be sent to? And the stabilizers, so the subgroup fixing a given vertex or arc. And the set of orbits, you can naturally think of it as a quotient of the original tree. So you get a graph, and it will always be a connected graph, which is formed from the set of orbits of the action. And just as a minor point, it's convenient for Serre theory to disallow the case of an arc being sent to its reverse. So you say the group acts without inversion. Um, and I'll just note that if that the stabilizer of an arc is contained in the stabilizer of its endpoints. Um, and the stabilizer of an arc also stabilizes its reverse arc. That's not too hard to check. Um, and so given a group action on a tree, um, you define the associated graph of groups to be the quotient graph decorated with representatives of the vertex and arc stabilizers, um, together with how you embed each arc stabilizer into um, a vertex stabilizer. Um, oops. Um, and then going the other way, you can define a graph of groups abstractly just as a graph equipped with some groups satisfying some reasonable conditions. Um, and given a graph of groups, you can produce an associated fundamental group, um, which comes with an action on a tree. So um, effectively, the fundamental group is produced from the vertex and arc groups with a presentation. Um, and the tree, the vertices and arcs consist of sort of cosets of certain subgroups of the group in a fairly natural way. Um, so so this all fits together quite nicely, and up to isomorphism, the process of turning an action on a tree into a graph of groups, and the process of obtaining the fundamental group of a graph of groups are inverse to one another. So this really sort of classifies all actions on trees. Um, okay, so this is a completely general approach to groups acting on trees. Um, and it's quite natural from the perspective of group presentations. Um, so the sort of idea with actions on trees from this perspective is that um, actions on trees are kind of free up to whatever the vertex and arc stabilizers are doing. So you can think of it as a kind of generalization of the amalgamated free product and HNN extensions. You sort of glue groups together in as free a way as you can, subject to the embeddings you've imposed on them. That ends up being what the fundamental group is. Um, but it does have some limitations, which particularly if you're considering you're trying to build examples of groups acting on trees. Um, that maybe have rather big vertex and arc stabilizers, or you've got some tree-like structure and you want to understand its automorphism group. Um, so the thing is, to build a graph of groups, you need to know how each stabilizer acts on the whole tree. You really need to know it as a subgroup, as a group. Um, so what if you only know how a vertex stabilizer should act on its immediate neighborhood? Um, So that leads us to the concept of a local action. Um, and given a group acting on a tree, the local action of a group at a vertex V, um, or let's say the local action of an individual element, is where you only look at what it does to, let's say, arcs coming out of that vertex. So this is what you see in the immediate vicinity of this vertex. Um, and given an arbitrary action of a group on a tree, you can define a certain closure of the group, which I'll call the P closure. Um, and for a locally finite tree, this is basically every automorphism of the tree such that at each vertex, it can be represented, the local action can be represented by an element of the group you started with. And just to avoid some problems with group topology, um, we define the P closure a bit differently if the tree is not locally finite. You want to only look at finite subsets of the neighborhood of a vertex. So for every finite subset of one of these inverse images of V, you have some element of your original group that does the same thing on that finite subset. And so then we say that G is P closed if G equals G brackets P. And just to make it clear, this is a closure operation. So if you take G brackets P, you get G brackets P. Okay, so, and it's always a group that you get as a result of this P closure. Now, these P-closed groups have the property P introduced by Tits in 1970. That's where the name comes from. I don't want to state exactly what Tits property P is. It's actually equivalent to this P closure for closed subgroups of the automorphism group of a tree. So yeah, it doesn't. It's slightly different for arbitrary subgroups, but I don't want to get into those technicalities. So the main theorem that the Tits showed was that if you have a group acting on a tree with property P, and the action is somehow irreducible, so it doesn't preserve any proper subtree, and it doesn't fix an end of the tree. So an end is like an equivalence class of forward paths through the tree. Then the group G plus generated by the arc stabilizers is trivial or simple. Now, this theorem was interesting. I don't know if it got so much attention at the time, but it was interesting as one of the first examples of a source of compactly generated, simple, locally compact groups that are not discrete, but are also not linear. So you think of like the simple Lie groups, those are all linear. And that you can construct analogous simple groups over non-Archimedean fields, which will give you more locally compact groups. But these were the first sort of non-linear examples, as far as I know, or certainly among the first. You can another way of thinking about local actions is to say, well, we look at a vertex stabilizer that induces some permutation group on the neighbors of that vertex or the arcs coming out of that vertex. You could start with some set of permutation groups and then try to build a group acting on a tree that has those permutation groups as local actions. So the same idea as the Serre graph of groups, except you're not specifying what the vertex stabilizers are. You're just specifying what they do to the immediate neighbors of a vertex. Now, there have been several papers taking this perspective, starting with a 2000 paper of Berger and Moses. So what they do is they only really consider locally finite trees. So think of a finite permutation group H. They define a group U of H, which has property P, and it acts on a tree transitively on vertices. So every vertex can be moved to any other vertex, such that at each vertex the local action is H. And they call it a universal group. As long as H is transitive, it is actually it's sort of the unique largest group with these properties. If H is not transitive, it's a little bit more complicated, but I'll talk about that a bit later. More recently, Simon Smith produced an analogous construction where instead of taking one local action, you take a pair of local actions. So a tree has a natural bipartition where two vertices are in the same part if they're an even distance away from each other. And so you specify one local action for each part of the bipartition. And yeah, Smith's construction gives you, again, the sort of universal group with these specified local actions. And he definitely considers locally infinite trees as well, because this is useful for what he was wanting to do, which is construct new examples of infinite primitive permutation groups that are locally isomorphic in the topological sense. So they have in the group topology, there's a neighborhood of the identity where different groups look the same, but globally they're different groups. So this is a very different setting to Lie groups, where knowing what happens in the neighborhood of the identity sort of tells you the whole group. That's not true for these totally disconnected, locally compact groups. And Smith's box product construction also has more general applications to the structure theory of infinite primitive permutation groups. So if you've heard of the Onan-Scott theorem, which is a theorem about the structure of finite primitive permutation groups, Simon proved a version of the Onan-Scott theorem for, let's get this right, so primitive permutation groups where the stabilizers have finite orbits. So this is a natural condition to consider for locally compact permutation groups. Okay, so I just wanted to give a brief overview of the background. Now I can get on to the main idea of our paper. So our goal was to obtain a systematic treatment of actions on trees specified by local actions, in the same way that Serre theory deals with actions on trees with given vertex and arc stabilizers. So in other words, we want to be able to extract from a group action precisely the information contained in its local actions, and conversely classify the universal groups with prescribed local actions. So what we came up with is a local action diagram. And this consists of a connected graph, gamma. For each arc of the graph, you need to pick a non-empty set, which we call the color set of that arc. And for each vertex, you need to pick a subgroup of the symmetric group on XV, where XV is the disjoint union of the color sets for all the arcs coming out of V. And moreover, you want each color set to be an orbit of the permutation group. So it should act transitively on each color set, but would also preserve each color set. So I might try and do an example. Let's see if I can do it. Okay, I'm not allowed to do multiple screen shares apparently. So okay, well, I can stop sharing my slides, and then start sharing here. Okay, so a local action diagram will look something like this. So you have some vertices and arcs forming a connected graph. And then for each, I guess I should draw these as arcs, but then I've got to remember which ones are the reverse of each other. So if I do them like this, and then like this. For example, So then I could have some sets here. Um, and let's say this has one arc coming out this vertex here, so this could be the permutation group 3, 4, 5. And then I could do something like that. This could be this permutation group, for example. And then let's say I put some sets of size 1 here, and I make this the trivial permutation group. Okay, so that's an example of a local action diagram. And there aren't any restrictions on this beyond the ones I said. So you have gamma connected graph. XA non-empty color sets. For each arc of the graph, and the local action which is some permutation group such that the XA are orbits of GV, where I'm taking those arcs that originate at V. Okay, so I'll go back to the slide. Oops. Okay, so given a group acting on a tree, it's easy to produce its local action diagram. So the graph is the quotient graph of the action, same as the Serre one. And then for each vertex, you take some representative vertex in the tree that's getting mapped to that vertex, and set G brackets V to be the permutation group induced by the stabiliser of that vertex on the edges, the arcs coming out of it. And then for each arc, you can take the color set to be an orbit of this group. So it's pretty straightforward to describe the local action diagram given a group acting on a tree. Then you can go the other way. So given a local action diagram, you can build a tree. And so it's a little bit fiddly because I want to say it's the sort of path, it's just a tree of all paths through the local action diagram starting from some base point. But that actually gives you, means that the vertices would have one too many neighbors if you do this. So yeah, let's see if I can draw a simple example actually. So I'll start again with the thing. Okay, so let's say we have 3 colors. So to draw a tree, and to draw the tree, I don't actually need to know what the local actions are. So let's say I start at this base point. So my tree would have a root, and then for each of the colors coming out of it, I'd need an edge coming out. Um, and now what I need to do is pick a reverse color for each edge from the color set of the reverse arc. So these ones are going to have a red reverse thing coming out of them. And then I do the next level. So at this vertex here, um, okay, maybe I should use another color. This is going to be a bit degenerate. Let's have another color that way. So this should have a red and a yellow arc coming out of it, but it shouldn't have more than one of each. So I would do that, and then I would do the same here. Um, maybe I'll do one more color just to make it not a line. So I do that. And I can just pick a reverse color pretty much arbitrarily. So I could make all of these blue, for instance. You don't have to do it in any kind of consistent way. Um, and then over here, these should have a blue and a green coming out of them. Well, that means I just put a green because I've already got the blue. Um, and then I pick some reverse color. Doesn't really matter which one I use. There's some arbitrary choices in this construction. Okay. But the point is at each level, I just need to pick some reverse color. And then at the next stage, I don't use that color going down, but I use all the other colors. Um, so, um, so basically the vertices here correspond to sort of colored paths through this local action diagram where I take a path, but at each point, or colored walks, I guess, because I'm allowed to backtrack. At each stage, I take an arc and then choose some color for it. Um, but I'm not allowed to sort of backtrack by using the same color. Um, I need to arrange for the number of out arcs of a given color to be correct. So there should only be one of each color, at most one of each color coming out of each of these vertices. Okay, so you build the tree like this, and this continues forever. So it's an infinite tree. Um, and then the universal group for um, this picture is basically if you take an automorphism of this tree, then the local action, if you look at like mapping a vertex to some other vertex by an automorphism of the tree, it will map the out arcs to the out arcs from you'll have a map from sort of O inverse V to O inverse W. But each of these has been colored in the same way. They have the same set of colors. So you get a permutation of the set of colors. And you basically take all automorphisms of the tree such that those permutations belong to the relevant groups G of E. So that's how we define the group U delta. Um, okay, so the coloring is just a way to consistently compare what's going on between different vertices. Okay, so go back to my slides. Um, okay, so here's the main theorem. Um, so up to natural kind of notion of equivalence, we have a one-to-one correspondence between local action diagrams and P-closed groups acting on trees. So given a group acting on a tree, if you form the local action diagram and then the associated universal group, then up to isomorphism, U of delta is the P-closure of G. And then going the other way, if you start with the local action diagram, form the universal group, and then take the local action diagram of that action, you get your original local action diagram back. So it's a correspondence. So effectively, this is a kind of classification of um, P-closed group actions on trees, as long as you're comfortable with local action diagrams. And the advantage of the local action diagram is that it really doesn't have any redundant information. Um, so in the case that the tree is locally finite and the action has finitely many orbits, then the local action diagram will be a finite graph decorated with finite groups and finite sets. So it's all just a finite gadget. So you have a recipe for describing these groups, which are usually uncountable, like they're non-discrete topological groups, in a finite way. So, for example, um, so with help from Stefan Tournier, we worked out how many groups there are. So, how many non-isomorphic um, P-closed vertex transitive actions there are on a tree of degree D, where D goes up to 11. And so the second column here is the number of permutation groups of that degree. So you have to consider all permutation groups of that degree, not just the transitive ones. And I think they've only been enumerated up to about 18 or 20 or so. It's quite hard work to enumerate all the permutation groups of a given degree. Um, but that second column tells you how many Berger-Moses groups there are of that degree. There's one for each permutation group. And the third column is the number of different groups acting on trees with that local action at every vertex and their vertex transitive. So you get slightly more of them. And basically, the difference between the two comes down to um, if you look at two neighbouring vertices, then the edge could belong to one orbit from the perspective of one vertex, but a different orbit from the perspective of the other vertex. So the non-trivial sort of structure here is in how you pair up the orbits between a vertex and its neighbor. So these are all given by basically a permutation group plus an involution on the set of orbits of that permutation group. Um, okay, but that's just a very special case. Like, there's no reason these groups have to be vertex transitive in general. Okay, so some special cases of this. So if you have a local action diagram, um, you can read off whether it has invariant subtrees or fixes an end of the tree. And I don't want to write down the full definition of what a scopo is, but basically there's some special structure. So it's a special kind of partial orientation of the edges, um, which corresponds to invariant ends and invariant subtrees. And in particular, if it doesn't have any of these other than the empty one, then you're in the irreducible case and Tits simplicity theorem applies. So a special case of this would be the following, which sort of characterizes um, simple groups under some mild assumptions. So if you have a faithful p-closed action on a tree with finitely many orbits, then so let's say you want it to be a simple group, and you want to rule out some sort of degenerate cases. So you don't want it to fix a vertex. You want it to have a translation in it. You don't want it to preserve any proper subtree. And there's a non-discreteness condition, which I've thrown in there. So there's no finite set of vertices such that if you fix those finitely many vertices, you fix the whole tree. So that's equivalent to the following condition on the local action diagram. So the graph is a tree. You don't have any leaves with where the color set has size 1. And each of the local actions is closed and generated by point stabilizers. And at least one of them is non-trivial. Okay, so that's it. If you satisfy those conditions, you've produced a simple group. And when I say closed, I mean in the permutation topology. So that means that the group is determined by what it can do to finite tuples. That's what it comes down to. So the permutation topology has base of neighbours of the identity consisting of these intersections of finitely many point stabilizers. Okay, so this is a pretty flexible source of examples of simple groups. So for instance, you could take some collection of closed transitive permutation groups with compact point stabilizers and draw a local action diagram in the just most unimaginative way. You make a star and you put these permutation groups on the leaves, put the trivial group in the middle. Then, and obviously the color sets will just be the whatever sets these permutation groups are acting on. So if these groups are compactly generated, then so is the universal group. And if they're each generated by point stabilizers by the previous theorem, then the universal group is simple. And moreover, it comes naturally equipped with a non-discrete, locally compact group topology. So this is some recipe that gives you you can sort of throw together finitely many permutation groups, produce a simple group acting on a tree that has those as local actions. And I'll just mention in a different direction, there's a preprint from a PhD student and someone at University of Newcastle and someone else at Newcastle, Stefan Tournier again. And they characterize what it means for a group with property P to be discrete. So they can certainly happen, but it's quite a special case. So another setting where P closed groups naturally appear is the following. So I want to give an example of a sort of fairly natural combinatorial structure that gives rise to a group acting on a tree with property P. So say a simple graph is one connected. So by simple graph, I just mean there's no multiple edges. It's one connected if it's a connected graph, but there's a vertex such that if you remove that vertex, it becomes disconnected. And say it's two connected if it's connected and doesn't have a cut vertex. Then a lobe of a one connected graph is a maximal two connected subgraph. So basically you should picture a bunch of lobes, these sort of two connected graphs that are stuck together in a tree-like way. So you don't have any circuits that sort of leave a lobe and then come back again. And what that means is that the graph gamma gives rise to a tree where you have vertices of the graph. You also have vertices for the lobes, and you make a vertex of gamma adjacent to a lobe if it belongs to if it's a vertex of that lobe. And so the induced action of the automorphism group of gamma on the tree is not necessarily the full automorphism group of the tree, but it is p-closed because all you really care about is what the local action at a lobe encodes sort of the automorphism group of that lobe. And then the local action at a vertex, you can more or less do anything as long as it sort of respects the structure of the lobes connected to that vertex. So in the special case, so the automorphism group can be represented as one of these universal groups of local action diagram. And if it's a vertex transitive graph, then the underlying graph for this delta will be, again, a kind of star, possibly with multiple edges, where the vertex in the middle represents all the vertices of the original graph, and then the leaves represent the lobes, with one leaf for each orbit. Now, I should say here we're not doing something particularly groundbreaking here. There was a classification of these graphs in the 70s. And many of these groups satisfy the theorem I mentioned earlier, so you actually get a simple automorphism group of the graph. On the other hand, given a collection of two connected graphs, you can stick them together in a tree-like way, and make that correspond to a local action diagram with the lobes at the automorphism groups of the lobes at each leaf. So we have a rich supply of sort of tree-like vertex transitive graphs that have a simple automorphism group. Yeah, maybe I'll draw one of these lobe graphs. Let's see. So a lobe could be something like this. Or maybe you could have a triangle. So this is what a typical lobe graph looks like. You have, or a typical lobe graph with a big automorphism group anyway. You have some repeating pattern of lobes, and there could be multiple types of lobe. I should say the automorphism group of a lobe doesn't have to be vertex transitive in order for the overall graph to be vertex transitive. So you could also have lobes looking like this, but then I've got to make sure that the sort of each orbit of vertices in the lobe is represented at each vertex. So if I do something like this, so this theta graph is not vertex transitive, but because of the way I've glued everything together, the resulting graph is vertex transitive. Okay, so there's lots of graphs like this, and as I say, many of them have simple automorphism group, which is kind of interesting. Okay, I'll go back to the slides. Okay, so the last thing I want to talk about is going beyond property P. Um, so the definition of P closure I gave earlier comes from a 2015 article of Banks, Elder, and Willis. But they're not actually concerned with property P per se. They're concerned with a more general property um, where you have groups specified by their K local actions, um, where the K local action describes, instead of looking at the ball of radius 1, you look at the ball of radius K around a vertex. Um, and they define the PK closure, um, with the P1 closure being the same as the P closure, and they prove an analog of Tits simplicity theorem. So you get a certain simple normal subgroup um, of one of these PK closed groups. Um, and so you might hope for a general theory of groups acting on trees in terms of their K-local actions. And interestingly, so this is sort of recent news. I think the archive preprint appeared in April or so, maybe end of March. Um, so there's a preprint which by Lena Lindorfer, Möller, and Vers, um, where they define what's called a graph of group actions. Um, and this is basically Bass-Serre theory, but for permutation groups. So it simultaneously generalizes Bass-Serre theory, which would be the special case of a group just where the groups just act on themselves, and local action diagrams where the permutation group is just the one local action. Um, and at least in the locally finite case, it looks like their construction will give you all the groups with property pk. Um, in other words, for every group acting on a locally finite tree with property pk, it will be the universal group of some graph of group actions. And I guess you could make them finite actions as well, which is maybe the more interesting point. Um, and I should mention there's also some earlier work by Stéphane Tournier, which is the sort of a version of the Berger-Moses universal groups, but for um, specified action on a K-ball around each vertex. But Tournier's groups are a bit of a special case. Um, so in particular, he has to assume that I think that the one local action is transitive and that for every edge there's some involution, so an element of order 2 that flips the edge. But under those assumptions, then his groups are universal in the same way that Berger-Moses groups are. So the GGA construction is not yet a full classification of groups acting on trees with property pk. So we're not in the same place as we were with local action diagrams. Um, so basically, to go beyond local action diagrams, you don't have the same with local action diagrams. The actions at different vertices don't really care about each other beyond matching up figuring out which color sets go on which arcs. But as soon as you go beyond P1 to higher K, you start getting compatibility conditions between the local actions at neighboring vertices they have to agree with each other on the sort of overlap between the cables. Um, and um, this manifests in graphs of group actions where you have these permutation groups associated to the arcs, and then you have these adhesion sets where they're glued onto the actions at the vertices, which is a bit complicated to describe. Um, and even for Tournier's special setting of these arc transitive groups he constructs, he gives you a compatibility condition for when a k-local action is compatible with itself, but it's a bit tricky to verify. So even in that case, we don't really know precisely what the possible actions are on k-balls. Um, and I should say even k equals 2 is tricky, like making sense of what these things are. Um, and another thing to say is that with graphs of group actions, there's no exact correspondence. Um, like there is with Serre theory and with local action diagrams. And that's in a sense because they're too general. And the way that they're set up allows them to have redundant information encoded in them. So I'm not sure it's been sorted out exactly what the sort of minimal amount of information is to produce, to extract from an action on a tree to give you the appropriate graph of group actions. Groups acting on trees with property PK still form an active research area with a lot of interesting questions. And the dream here would really be to develop a theory of K closed actions where you can sort of let K tend to infinity. Because actually, if you have any closed subgroup of ORT T, then its K closures form a descending chain whose intersection is the group you started with. So in principle, everything can be approximated by, looking at the K closure for larger and larger K. And yeah, hopefully, I'll work on P closed groups is a good starting point for this more complicated theory. Okay, so I'll just leave you with some important references, and thanks for your attention.
Thank you, Colin. Do you have any question on the talk? Yes.
Can you hear me, Colin?
Yeah, just about.
Yeah. So you've got these two constructions that go in two directions and they kind of undo each other up to some kind of isomorphism. Is there a categorical way of saying this? Like, is there a category of lands? And are these things functors or something like that?
I'm sure there is, but we haven't written it down. Yeah, I mean, yeah, the thing is that the way we construct the universal group is not very canonical. That's the only hesitation I have. Yeah, I don't know. Yeah, I haven't thought about making it a sort of categorical, functor or whatever.
Is the Serre stuff given in functors?
Yeah, probably. I mean, that one is a bit more canonical, I think, because you really construct the tree as consisting of sort of a disjoint union of a collection of coset spaces. You don't need to make any choices.
Thanks.
Any other question? Any question from online? Hi, Colin. I have a question about the PK case.
Yep.
For the PK case, I noticed that for P case, you color like the edges or what you call the arcs with some specific color. For the PK
Yep.
case, do you require that the K edges are colored with the same color, or it's okay they are with different colors?
I don't remember exactly how they do it. I think what they do is they do things a bit differently. So that they're starting from the graph of group actions, they build what they call a scaffolding graph, which is not exactly a tree, but it's sort of one of these tree-like graphs. And somehow that's built in such a way that it carries all the information that you need to remember which things need to be compatible with each other. And then you can sort of extract from that, and the automorphism group of this scaffolding graph then acts on a tree in a natural way, and that gives you the universal group you want. So yeah, it's a bit of a different approach, I think.
Thank you. Any other question? If there's okay. If it's no more question, let's thank Colin again.